We are very happy to have with us today Alex Cohen. Alex is currently a PhD student at MIT, and in my personal opinion, one of the big promising stars at the moment. So you can tell later that you knew him before he was famous. What should I say? Alex actually affected me quite a bit the way I see what research undergraduates can do. It was in one of my first years where I did a summer research program as an undergrad. And he just kept solving more harder and harder problems. And eventually had, as an undergrad, something that was published in the Duke Journal of Mathematics and Quanta. So that was a long time ago. Today, he's going to tell us about a more recent result that was also recently on Quanta, though. So I think I'm done embarrassing him, and you can start.
Thanks, Adam. It's not fair because I never got to embarrass Adam back. Maybe in the future. Okay, so thanks everyone for coming. Today I'm going to talk about Heilbronn's triangle problem and connections to projection theory. So not the problem right now, but something that I think is fun about this area is it's a very simple to state problem in discrete geometry, but we end up bringing in some recent tools from analysis and building some new connections there. So that's what I'm going to hope to tell you about. Okay, so here's the problem. Start by placing n points in the unit square, okay? Okay. So for any set of n points, the question is about finding small triangles in this set of points, small area triangles. So this is not actually the smallest area triangle, but it's one I can draw. And I'm going to let delta p be the smallest. Can everyone see and everything? Okay. And delta of n is, I'm going to write the words and then just say out loud what it is. Okay. So I'm just going to say it as a sentence. Oh, delta of n is the smallest possible number, so that for any set of endpoints, no matter how you place them down, we can always find a triangle with area less than delta of n. Okay, so delta of n is going to go to 0 as n gets larger, and the whole game is about finding small triangles. So, okay, we want to understand this quantity delta of n, and there's kind of two games we could play. We could try and prove lower bounds and upper bounds, and in this talk, I'm interested in upper bounds. So the problem is to find asymptotic upper bounds. I want to give everyone a moment just to digest what the problem is. You know, maybe scribble on your paper, like if you were trying to design the set of endpoints so that the smallest triangle has the largest possible area, how would you do it? I'm going to give everyone a moment to think about it. I've noticed it's simple to state, but it's a little bit hard to like digest.
What points can be on the boundary?
They can be on the boundary. Yeah, that's fine. Okay. So lattice. Okay, so lattice is a nice idea because it's spread out, but a lattice is actually going to have delta equals 0 because it'll have 3 points on the line, and 3 points on the line will have triangle area 0. So that's a good example. A perturbed lattice is a good idea. Yeah. Okay. So here's a first observation. This is an easy upper bound. Okay, so I'm claiming that in any set of n points, we can find a triangle with area less than 5 over n. Here's how we do it. Okay. Take our big square and split it up into strips that have area 5 over n. Okay, by the pigeonhole principle, one of these strips will have 5 points in it, right? Here we're going to draw this out. And so if we just take one of the strips with 5 points in it, connect 3 of them, the area of the triangle is less than the area of the strip. So your triangle is less than 5 over n. Okay. So this is an easy upper bound. There's several other ways to prove this. And so if you're interested in asymptotic upper bounds, the first interesting question you can ask is, can you prove something better than this asymptotically? Are there triangles of area less than 1/n asymptotically? That's the first interesting question. Okay. The second observation.
Can I ask a question?
Yeah.
Why does this argument work for field?
It works with 3/n too. I don't care about the constant because asymptotically I'm trying to ignore constants, but the best you could sharpen this to get like 1/n minus 2 or something. Yeah, good point. Okay, the second observation is about how this problem scales. So if you're thinking about how you put down this set of points, the points might look like they're completely spread out, or they might look like they're clumped together more in some places than others. And scaling is the observation that if the points have some extra density in some locations, you could make use of that to find small triangles. So, okay, I'm not going to do the formula, but just try and get the idea. So, okay, this is an arrangement of points where there's an extra density over here. And the idea is that if we just look inside this little box, we're faced with the same triangle problem inside a smaller box, and we can then kind of take this thing and scale it up. And we can just run the problem again in this smaller square. And so the idea is that if there's an extra density of points in certain regions rather than others, we can just try and find a small area triangle only in that region, and we can do a little better. So in particular, if all we want to do is improve over this easy bound, then like any increased density over the expected amount, we could run this little strip argument again to find a smaller triangle. So once we, that's a scaling observation. Okay. Any questions so far? So now I'm going to describe the prior upper bounds. Oh, I realized I forgot to mention something. I'm going to mention it here. So if you Google Heilbronn triangle problem, it's actually more famous for some work on the lower bounds than the upper bounds. So Erdős proved with an explicit algebraic construction that you can find, he actually constructs an explicit set of endpoints where every triangle has area more than 1/n squared. And then, that was Erdős. And then Cohen, Hinz, and Samaretti gave a logarithmic improvement with some significant combinatorial ideas. I'll write their names out later. Okay. So we're going to focus on upper bounds, not lower bounds, but it's helpful to keep in mind, right? So far, we know that the true value is somewhere between 1/n and 1/n squared. Okay.
Did they make any conjectures when they did that?
The only person who made any conjectures was Heilbronn, who conjectured 1/n squared, which Cohen, Hinz, and Samaretti disproved. And since then, people haven't really spent much time conjecturing. So
Too scared.
well, people are too scared to conjecture, including me. I'm too scared to conjecture. Okay. So easy bound is 1/n. The first improvement was given by Roth, who gave a very slight improvement. So, okay, I said the first interesting question was to improve on that bound, and Roth did that. And he used a density increment argument, which has a similar flavor to his argument about 3-term arithmetic progressions. Okay, so then there was nothing for 20 years until Schmidt. Schmidt liked to write papers following up on stuff Roth did and keeping ideas somewhat. So he did that in this problem too, and he proved following that. So in this log of log, he shaved off one of the logs. So it's a lot better. This is a much better bound and it's a much simpler proof. This is great. People are really excited about this. And Roth must have been inspired by Schmidt to come back to this problem. And in the next year, he proved a huge improvement. He proved a power saving bound. So this is a very significant quantitative improvement. And he introduced an analytic method to prove upper bounds. And this is where all the work since then, including ours, builds on the method that Roth introduced. Okay, so since then, Roth wrote like 3 more papers. He got a little bit obsessed with it, where he improved the bounds a little bit. And in 1981, Komlos, Prince, and Samaretti gave the exponent 8/7. Okay, it's hard to tell just from looking at an exponent what the significance is. I'll try and explain the significance of this exponent later. But in some way, this is a natural limit of what Roth is doing. Roth didn't write down the number 8/7, but I think he knew that number and was kind of going for it. And so what we did is we improved this almost Samaretti bound by a little bit.
For 40 years, there was no progress.
Yes. Okay. So now I'm going to try and describe to you what this method is that Roth came up with here. And I'm going to try and explain Roth's method in kind of a modern language. And then in that language, it'll kind of appear natural what tools we're gonna end up needing. Okay.
And that's what you refer to as serious analysis coming in.
Yes. Okay. So here is Roth's setup for the problem. Okay. So we start with a set of points P inside the unit square. And what we're going to do is we're going to take all the pairs of points that have distance u. U is some parameter to be chosen later. Think of it as like n to the negative 1/3 or so. Take all the points at distance u and draw a line through them, connect them. Okay, and then we get some set of lines. Now I'm going to define a quantity.
Oh, I can't quite see that. L is what? Is this
L consists of all the lines connecting pairs x and y that have distance less than u.
Okay.
So here, okay, so by the way, I'll just explain what we're doing before I write more equations. So if you think about finding a triangle with small area, one thing you could do is you could look at all of the triples of points, and you could find some triple with a small area. Okay, so when I first wrote the problem, that's kind of what I tried to do, and it's kind of hard to do that. So instead, we're going to pick 2 points first that are from the base of the triangle, and then we're going to find a third point to form the height. And we're going to use the formula area equals base times height.
That's not the hard analysis.
That's not the hard analysis.
What are x and y?
So x and y here are a pair of points in the set P that have distance less than u from each other.
Okay, like for any pair you pick out.
Yes. Sorry, I missed some words in that. Okay. Right, so the reason these lines are significant is because if you pick this to be your base and some third point over here to be your third point in the triangle, the area is given by this distance u times the height from the third point of the line. So the line describes how to find the area a third point makes for that pair. So here's just some more notation to encapsulate this idea. Okay, so read this as the number of instances at scale W. And this is, so we have some set of points P, some set of lines L, right? So P is the point set we started with. L is this line set we built out of our point set. And this quantity I is the number of pairs that are at distance less than W. Right, and so the quantity depends on W. So, for instance, right, what we're doing is we're looking at these little W-wide tubes around all of the lines we made and counting how many points there are on each of them and summing up. Right, and if even one of these tubes has some third point in it, then we know there's a triangle area less than U times W, right, using base times 10. Okay, so this is going to call the incidence formulation of the problem. Okay. So W final is some other parameter that we're going to choose later. If the number of incidences at scale W final is bigger than 2 times the number of lines, then one of these little tubes has to have more than these 2 points in it that we made it from. And there's we can make some triangle out of a pair we started with plus a third point. We can give you a sense of the parameters. We could take. This is similar parameters for like one of Roth papers. Okay, so if we choose U as n to the negative 1/3, and we can find the goal with W final equals n to the negative 3/4, then we'll find some triangle area n to the negative 13/12, which is a power saving bound over the. Okay. So Roth's initial paper also used a setup kind of like this, where everyone uses pick the base first and then the height. That's what everyone does. There's a difference though in that Roth and Schmidt's papers kind of have to pick many different scales W here. And it has to do with synthesizing several scales. And Roth's 1971 argument doesn't do that, it does something else. So Roth came up with a 2-step method in order to include this goal. The first step is an initial estimate. Okay. And the initial estimate, so we need another parameter. There's 2 parameters now. There's W initial and W final. W initial is a big scale. Think of it as like n to the negative 0.01. W final is a small scale. Think of it like n to the negative 3/4. Maybe I'll just draw. This is the big scale, and this is the small scale. The initial estimate is about proving that there are lots of incidences at the initial scale. Okay, so let's just look at this right-hand side for a moment. If the points and lines were distributed randomly, then for every line, the number of points within distance Wi, you'd expect to be like Wi times size of P. So this is the number of incidences you would expect if the points and lines were distributed uniformly at random. Okay, so the initial estimate is about proving that there's at least as many incidences as we would otherwise expect. Okay, so it's a pretty strong claim. And the catch is that we're proving it for a very big initial scale that isn't going to be directly useful to us for finding small particles. Okay, the crucial aspect is in the inductive step. This is kind of the heart of the analytic method that Roth introduced. So the inductive step, right? So these quantities are a normalized incidence count, right? If the number of incidences is like the expected number, both of these are going to be around 1. And so the inductive step is about proving the normalized incidence count doesn't change much as you vary the scale parameter W, right? So if you make these tubes thinner or thicker, it doesn't change the normalized incidence count. So this is really a dramatic step to take. It's a mean value kind of thing rather than like an extreme kind of thing. So, right, it turns out we only need to find, a small number of incidences. We only need to find one extra point in one of these tubes. That turns out to be hard to do because it's like an atypical thing. So Roth's idea is instead try and prove there's lots of incidences, and that's an easier thing to induct on and prove happens in a robust way for several scales. Okay. Any questions so far? Yes.
Sorry, maybe I just didn't catch. At the bottom, you're multiplying U, W, you're getting something more than the product? Or is you're getting minus 13 over 12 instead of...
Did I do the product wrong? This is, right, that's 4 over 12. And that's 9 over 12. So isn't that 13 over 12? U times W?
Oh, okay, sorry. Oh, it's the product, got it.
I hope I didn't do that wrong. That would be a problem.
So this is just an example of if you could prove that both of those things.
Yeah.
So that way, then you get, okay.
Right, we're not going to actually use these parameters. It's just an example of some parameters you can take.
Thanks.
So Roth had some really, so by the way, Roth is a funny mathematician. Roth only wrote a few papers. Most of the papers he wrote started a field. This one didn't, but I think it should have. He had some really good ideas in this paper. In these works. Okay. Okay, right. So these two steps. So now I can kind of explain this history a little bit better. So in Roth's first paper, he had some initial estimate and some inductive step. And in all of these subsequent papers up through 1981, so including Cohen and some Reddy's, they kept the same initial estimate and they kept on refining the inductive step. So really the improvement was in kind of the way you pigeonhole things and some kind of, it was kind of a technical thing that was getting improved, which is why I think Roth had that 8/7 in mind. So Roth kind of figured out a few ways to make that better, but he was getting hung up on a few things, and Como Pinto has already figured out how to do this without too much loss. And so with Roth's initial estimate, you really can't do better than 8/7. So our improvement comes from improving on the initial estimate and keeping the same inductive step. Okay. So here's the main idea I want you guys to talk. We're going to analyze finite sets of points using fractal geometry, using ideas coming from, this is where the analysis comes in. So, okay, I don't know what would be the right place to go back to, but at least one place this idea goes back to analyze finite sets of points using ideas from fractal geometry, goes back to Katz and Tao, who introduced a bunch of ideas and problems related to this. And there's been a lot of activity in fractal geometry recently. A lot of good conference is here. And So we're going to end up using some pretty serious stuff for fractal geometry. So both steps get a reinterpretation in terms of new ideas. So Roth's inductive step turns out to be essentially equivalent to something called the high-low method. To the Guth-Stallman one. Okay, so Roth came up with his inductive step in 1971. The high-low method came out in 2017. Roth used his inductive step to prove lower bounds for incidences. Guth-Stallman and Wang used their high-low method to prove upper bounds for incidences, but it's the exact same method, and they both prove something more, which is that incidence count is the expected number. So this is not where our improvement comes from, but it's a neat connection. Roth actually wrote in his paper, something like, I hope that these ideas will have more applications to discrete geometry. And so 50 years later, that was definitely came true. The initial estimate, this part is not a reinterpretation. This is really a different method. This is kind of the more important part. And we are going to prove initial estimates using direction set estimates from projection theory. Okay, so this is about saying you have a finite set of points, look at the set of directions that set of points spans, and proving that set of directions is spread out. Somehow that's the key ingredient to proving these initial estimates. Okay. Any questions so far?
2017.
Yes.
Okay.
Decide how much I want to tell you about the thing we did versus the thing we didn't do. But I want to tell you the highlights. It's cool. Maybe I'll just state it and not talk much about it. Okay. So, okay, in order to prove something like this, we need some hypotheses about the points and lines. It's not always true. And we're going to need a pretty robust ingredient, which is some information about how much the points and lines get concentrated in any place in the square. These are the relevant quantities that's going to contribute to our estimate. MP is the maximum number of points that can concentrate in a W by W square. And ML is the maximum number of lines that can concentrate in a W by 1, 2. Okay, so just to clarify, right, what does this notation L intersect P mean? What I mean by this is all of the lines where if you cut that line off to this unit square, it lives inside of this W tube. So T ranges over all of the W tubes, Q ranges over all of the W by W squares. Okay, if everything is distributed uniformly, we expect this guy to be around W squared times the number of points, and this guy to be W squared times the number of lines. Okay, the thing we're estimating is exactly right, exactly everything we want to estimate. So, okay, you can play with this yourself and kind of see how it behaves, but the main point is that the change in the normalized incidence count is controlled by an error, and the only ingredient to the error are how much the points and lines are concentrated. Okay, I'll mention one little thing, which is when Roth first came up with this, he applied it to like boom WI, boom W final. He just applied it with the real W initial and W final of the argument and got something. And then he realized later that it's actually, this argument benefits from applying it several times at several scales. And so that's the way we do it in the modern way is we'll take W final to be like W initial over 10 or something and apply it like logarithmically many times. That took Roth a few papers to figure out. Okay, so I'm just going to state the main idea in proving this is to write down this quantity, this change in incidence count, as an inner product of two functions, one function coming from the points, one function coming from the lines. And the function from the lines will have a positive part and a negative part, right? The positive part corresponds to this, and the negative part corresponds to this. And the average value is 0. And the idea is to use Cauchy-Schwarz and orthogonality. So we split up this inner product into a piece that just has information about the point, is just information about the lines. That's why there's, some kind of product thing happening here. And the main idea is to use orthogonality. It's called the high-low method because the Fourier analysis interpretation is to think of this as decomposing into high frequencies and low frequencies.
I maybe don't fully understand this W to the -3 down the bottom here. Which W is that?
Okay, good question. Good question. I'll make it W fun, because that's the one that makes it bigger.
All right.
Right. In practice, when we apply it, it doesn't matter because we're going to take both W's to be off by a factor of 12.
Okay.
And then it's just W. But, question. Any other questions? This is coming through. So okay, I'll mention one other thing, which is we need to actually have these ingredients to apply this. So, okay, the line regularity comes from other pieces of the argument, and I can't fully explain it right now. But the point regularity, we already discussed where that comes from. That comes from the scaling observation. So here's the idea. If the points are concentrated in some region, just look in that region and find a small triangle there. Just run your argument in that smaller region. And if they're not, that's exactly the ingredient we know the incidences behave as we want them to. So that's where the scaling observation comes into play. So what argument we do, right, it's kind of encoded in the argument, it's a little hard to unpack, but exactly where we apply this argument depends on how the points are arranged. So the way the points are distributed is an important determinant of the argument.
Right, and is there not like a similar kind of scale / density argument for these like lines? If you had a bunch of dense lines, could you not just like, scale it up vertically or something like this? Like, feels like it's the same kind of argument for the two different classes of objects.
Yeah, no, that's a great point. And you will have to do something like that. You will have to do some kind of scaling, but it's not quite as straightforward because if you scale with the points, you get the exact same problem over again. So it's just a bunch of points and finding a small triangle. And with the lines, if the information you have that there's a higher density of lines in that tube, that's less straightforward piece of information to apply apply the argument again. Sure. So there will have to be some argument like that, but it's not, it's a little bit different. Because remember, the lines, there's more lines than points, and the lines are defined by the point set somehow. So the argument is not symmetric in the point set and the line set. So I'm trying to explain. I mentioned before that the initial estimate has to do with direction sets. So I want to explain that connection. There's a few parameters in the argument, so it's a little hard to keep track, but importantly, the parameter W initial in the initial estimate is bigger than the parameter U, which is the length scale of the pairs we're picking. Okay, so here's how that is relevant. So I'm going to write the line set. Okay, so I'm ranging over all of U by U squares Q. And I'm forming line set by taking each of those U by U squares and then connecting every pair of points inside of that, because every pair of points will have distance like U. Bad Q is going to be the set of directions. Okay, it's a subset of the unit circle associated to every U by U squared Q. It's a set, so, okay, right, we'll just say, okay, here's what we're doing in the initial estimate. We take all of these pairs, we take the line through those pairs, we take a big WI by 1 tube around that line, and we count up all of the points inside of that tube. And the good thing that we want to happen is that all of these tubes have the expected number of points in them. Okay, and if that's true for all of these lines in our set, then the total number of instances will be the expected number. So the bad thing we want to avoid is that of all on the tubes that we make, like most of them having much less than the expected number of points. That's the bad thing. Okay, and the reason this observation that WI is bigger than U is important is right? The line is determined by like its direction and its offset. But if we look at just pairs within this little square Q, the offset is at scale U. I realize I'm saying letters a lot. The offset is much smaller than the total width. So the offset doesn't really affect the tube very much. We can kind of ignore it. So the only relevant thing for looking at this tube, if we know our pairs inside Q, the only relevant thing is the direction that that line makes. Okay, so the bad set of directions is a set of theta, direction theta, such that this is the set of directions where the tube in that direction has not many points. Okay, the direction set of theta of Q is the set of directions formed by a pair of points in Q. So let's say that the bad set for Q is like these two tubes. Then the bad thing we want to avoid is that all of the directions land in this small number of bad tubes. That would mean we don't have a good initial estimate. So there's two ingredients to rule out this bad scenario. The first one is kind of an easy ingredient that comes from a double counting argument, which is that the set of bad directions is small on average. This is some kind of double counting argument. Okay, so for most of these squares, we can just assume that basically for all of these squares, the set of bad directions is very small compared to the set of all directions. And the second ingredient is that the direction set is spread out. Okay. So that's how we're bringing in direction sets. If you know the direction set is spread out, then that means that we can't concentrate in this bad set of directions. And that's what we proved in this last minute. And this is a different method than what Roth and company did. Okay. Any questions? All right.
What do you mean by direction set is spread out?
I haven't defined it. It's a good question. Here's what I'll mean. I'll mean that the number of pairs where the direction kind of lands in this WI region, an upper bound on that number. An upper bound on the number of pairs where the direction lands in some region. So it's a kind of anti-concentration kind of thing. The shown directions aren't too concentrated in any interval.
So like this happens for any generic kind of thing.
So the hypothesis we need on a set so the direction set is spread out is that its fractal dimension is large enough. That's where the fractal geometry thing comes in, is that we need to know the set is big, and the way we need to know it's big is in terms of its fractal dimension. So Mercer wrote a paper in 1951 that initiated proving a lot of theorems like this. Suppose you have a set whose fractal dimension is such and such, apply some operation to it, map that set, from R, B to R, and whatever. How big is the fractal dimension of the image? He proved a bunch of theorems like that. So one of the theorems he proved was about the direction set, which is, okay.
X is subset of the Q.
Yes. Okay. So I haven't defined Hausdorff dimension, but we're not going to end up needing it. But the hypothesis, okay, the maximum dimension of direction set is 1, because the direction set is a subset of the unit circle. So this theorem says that if the Hausdorff dimension of this set is bigger than 1, think of the Hausdorff dimension as something about the size of the set. It's a multi-scale way of saying the set is big. Then the direction set is big. Okay, and so in particular, a discrete version of this theorem is the necessary ingredient to prove the 8/7 bound. That's where this 8/7 bound comes from, is somehow needing the points inside of these little u by u squares q to be greater than one-dimensional. So in order to improve on Roth's initial estimate, we need a direction set estimate that applies when the dimension is less than 1. And Marstrand didn't prove anything like that. Okay, Hong Kong correct me if I'm wrong here, but I think the first good result like that was by Orpinen in 2017, who proved that, for instance, if s equals 1 or like 0.99, then the direction set has dimension at least 1/2, which is something. And but okay, well, anyways, there's a very sharp theorem about these things proved in 2022 by Thomas Orpinen, published Morgan, and Heilbronn. Right, so actually, so there's a good reason that this thing fails if the dimension of x is less than 1, which is x could be a line, x could be contained in a line. And if x is contained in a line, the direction set has just 1 point, which is the direction of the line. So in order to prove anything, we need to assume x is not contained in a line. So that's the hypothesis. This statement is a very nice hypothesis. That Hausdorff dimension of x is something and it's not contained in a line, then the dimension of the direction set is at least s. Sure. Mess up the statement, so mess up the punchline. So this is the sharp results about direction sets. And this theorem was the culmination of a long and significant line of work. And at the base of that line of work is Bourgain's discretized sum product theorem. So there's a good reason that we need to use the sum product theorem in this direction set theorem, which is that it's not true over the complex numbers. And the sum product theorem distinguishes the real and the complex numbers. So this came out basically just in time for us to use it. We started working on this problem in like September 2022. We figured out we needed this in like January, and they worked it in like September. So somehow really things just aligned, which was nice. It could have if we worked this year earlier, we could have written down the statement that we needed to be like, all right, well, that thing's hard. So it was lucky that this got proved in time for us to use it. And
Could you say again some of the book that Bourgain that's behind this?
yes,
Say that again.
so this is part of a whole line of work in fractal geometry. And the thing that's the top of that line of work is Bourgain's discretized sum product theorem, which says that if you have, for instance, it rules out the following. It rules out the possibility of a set with Hausdorff dimension 1/2, subset of the real line, such that the sum set and the product set both also have Hausdorff dimension 1/2. Right, so yeah, that qualitative version was proved by Erich and Volkmann, and Bourgain proved the discretized version. So this, right, okay, so when I gave talks since before, this was like the latest best thing in fractal geometry, but since then, this was an ingredient in proving the Furstenberg set conjecture, which was done by a big piece that was done after this by Orpin and Schmerken, and then the rest of it was finished by Hung Wang and Kevin Wren. And so this is an area that's really exciting right now. And it's I think really cool that we get to borrow some of their ideas to say things about triangles. Okay, let me see. Okay, so I'm going to take my 2 more minutes to state something that I promised Hong and I would like that. This one, which is, so we've kept working on these things since then. And all right, so I wrote in the abstract there were 3 different connections to projection theory. So okay, the first one is this. The second one is the initial estimate. The first one is second one is the initial estimate, and the third one is being a little bit cheeky. The third one is that Heilbronn's triangle problem. It turns out to be a problem that lower bounds for incidences. Sorry, not obvious from looking at it, but that's what it turns out to be about. And there's been a lot of work on upper bounds for incidences in various settings. And this triangle problem, kind of tells us to look at other problems about lower bounds for incidences. And it turns out there's lots of other interesting problems we can write down about lower bounds for incidences, and there's some connections between them. So we started working on other problems of this sort, and here's an example. Okay, so say that you have a set of points and lines in the unit square, and they come in pairs. So points and lines. The theorem says if you have a set of points and lines created in such a way, then there always exists some non-trivial pair that is non-trivially close together. We can give you a sense of where this. So the easy bound of those problems n to the negative 1 half. And that corresponds to the trivial bound for the triangle problem. The non-trivial bound that we proved is 4/7. And this actually implies in a pretty easy way the Cohen's and summary bound. All right, to do it, take your points, split it up into little pairs. Okay. At best, you can make n pairs that are the distance n to negative 1 half. Find some non-trivial third pair, and boom, that makes a triangle with area that's an n to negative 8/7. Okay, it's possible I said that wrong. Let me just say it does correspond to n over negative 7, but it might make it in a more complicated way. And there's another significant exponent, which is n to the negative 2/3. And this is kind of the best possible exponent you could prove using the high-low method if everything was distributed exactly as you'd hope. Basically, if you could prove the right initial estimate, which is the hard part, then this is what the inductive step is. And if one could prove this, this would correspond to a significant exponent for the triangle problem, which is n to the negative 7/6. And this is also kind of the best possible exponent for the triangle problem if everything breaks your way when you're trying to apply the initial estimate in the high-low method. But there's a barrier below that. So it's kind of an interesting thing that we're able to prove this thing that matches up to the Cohen's summary bound. And so something we're working on right now is trying to improve this n to the negative 4/7 exponent using different ideas, which would lead to a different way of improving the triangle problem, hopefully with better bounds. So anyway, that's all I wanted to say. Thanks for coming.
So is the last line a conjecture or
This is the conjecture.
the other was a proof?
Yes. Yeah.
Okay.
This is the conjecture. And there's something nice about this problem is, Evan, you pointed out that we should also use induction on scales to prove line regularity. And I said that something that's a little bit annoying is that the points and lines aren't symmetrical. But in this problem, the points and lines are symmetrical, which is nice. And induction on scales works a little bit better for that reason.
But on this one, because you have an improvement on n to the -8/7, but you don't have an improvement on n to the -4/7. Right?
That's right. So far. Right. So it's, this is a problem you might, if you have a theorem about upper for incidences, it might say, suppose the points are concentrated like this, and the line is concentrated like this, and the number of incidences is less than this. And you can't have a theorem like that for lower bounds, because you could have something like the points are all in the upper half of the square and the lines are all in the lower half of the square. And then there's no incidences. So there's no non-trivial lower bound. So you need some kind of hypothesis to rule that out. And one of the significant differences between upper and lower bounds is that, right, if you prove an upper bound, then kind of your initial estimate and your inductive step will just give two contributions to the error term. And, they might be of similar order of magnitude, but they just give two things and you can get something. But for lower bounds, if your error term from the inductive step is bigger than your error term from the initial estimate, you get nothing. Because if you have like a minus b and b is bigger than a, it could be 0. So that's kind of the thing that makes it different from other problems is the initial estimate.
So here, how do you get the Hausdorff dimension estimate on these little boxes, the points in these little boxes?
That is a great question. So, all right, first, since you've given me a question, I'm going to take opportunity to write down the actual hypothesis that we use, which is the discretized version. So the actual hypothesis is something called a Crossman regularity hypothesis. So here, Q is some square with W, and W is bigger than delta, and it's an upper bound on the number of points in one of these squares. So if you had an upper bound like this at some scale W, that would be like saying the point set is big at scale W, and the significant thing about a Frostman regularity hypothesis, it says that the set is big at every scale. And that's the type of thing that you need in order to get results like this, because if the points that were big at one scale and small at another scale, that would still be bad for something like this happening. So anyway, this is the type of hypothesis we need, and it's the same scaling type of observation is the way that we get it. If this were failed to be true, then we could just look inside the square Q and find a small triangle there. No, it could go all the way down to n to the -1. I think there's a good chance it does. But n to the -2/3 is kind of a limiting scale for the high-low method. But it could be that it goes all the way up to n to the -1, which would correspond to a better bound, n to the -3/2 for the Heilbronn triangle.
You've set this up so that it's all centered around unit squares. Supposing you looked at regular polygons of a fixed area, does this imply similar results, or is the world different there?
It's all the same up to constants, because if you have any, if you have any other convex body, you can apply some transformation so that it looks approximately like a unit square. Like if you have a really thin and long triangle, use John's one, whether you can always put an ellipsoid inside and outside, and then you can map those to some circles. So because because the problem is invariant under any affine transformation. If you care about constants, then it doesn't matter. If you don't care about constants, then it doesn't matter.